So in this video, we're going to talk about the limiting reactant, theoretical yield, and percent yield. And before we even tackle the general idea and a problem to just show you how we work these problems, we should know what they mean. Okay, and so limiting reactant is the reactant that is completely consumed over a chemical reaction and limits how much of a given product you are able to make. So in fact, what it means is that which one of those reactants you have the least of, okay? Okay, theoretical yield is the maximum amount of product that can be made and is always based on your limiting reactant. Okay, so your theoretical yield is always based on your limiting reactant. And the percent yield is simply something we have to remember. We got to remember that it's the actual yield divided by theoretical yield times 100%. And so we need to tackle a problem, okay? And I promise you, this type of problem, this will work all across the board for any problem you're tackling with percent yield, limiting reactant, theoretical yield. This is a process, okay? So usually you're given a balanced chemical equation, okay? So in this case, we have 10.0 grams of magnesium that reacts with 10.5 grams of oxygen gas, okay? And that gives us approximately 11.9 grams of magnesium oxide. Magnesium 2 oxide, okay? And so here's the deal. The first thing I usually do is pick out my actual yield. And usually your actual yield is always given in a problem, and it usually states that, okay, well, some product is collected or you recover. Okay, so that's another word. So look for recover, this amount of product or this amount of, so collected, recover. Those are some buzzwords that will always give you the fact that that is your actual yield. Okay, your actual yield is something you do not calculate. It's always given. Okay, and so in fact, I'm going to underline this, that I have 11.9 grams of magnesium 2 oxide that is collected. So that's my actual yield that I actually gained from the reaction itself. Okay, so how do we go about finding a limiting reactant? Well, the limiting reactant, as it says, it's a reactant and not some decimal or number. It's a reactant. So which one of these, okay, is it magnesium or oxygen? Well, to do that, we have to find out. And so how do we do that? The first thing we do is convert to moles. Okay, so I'm going to take 10.1 grams of magnesium, 10.1 grams of magnesium, okay, and I need to go to moles of magnesium. Well, how do I do that? I look at the periodic table, and so for every 24.305 grams of magnesium, I get 1 mole of magnesium. Okay, now I need an extra step here, and this is where I want you to. This is where a lot of people forget. Okay, once I get to moles, I need to relate how much magnesium I have to the amount of product that I'll be getting. Okay, I need that, and essentially we're getting the moles of product. The moles of product we're getting from each reactant. We're getting some moles of this from this, some moles of this from this. Okay, and so now that my reactant is in moles, I'm going to look at my chemical equation, and here's the rationale that I'm going to make. For every 2 moles of magnesium, I get 2 moles of magnesium 2 oxide. Okay, and so how do I write that? For every 2 moles of magnesium, I get 2 moles of MgO. Now in this case, 2 divided by 2 is just 1. So in this case, it would not have mattered, but you need to show this type of work, okay? And so notice that my units will cancel out. Magnesium cancel out with magnesium. Magnesium cancel out with magnesium to only give me magnesium 2 oxide, which is exactly what the amount of moles we need. Okay, and so if we plug this into our calculator, okay, so if we plug 10.1 divided by 24.305 and multiply it by 2 and divide that by 2, in this case this is just 1, so it wouldn't matter, so this would be approximately 0.415 55 moles of MgO. Okay, now be careful of significant figures here. Notice that we're multiplying the amount of sig figs that you come out with is always which figure has the lowest amount of significant figures, and this has 3. So in fact, I'm just going to put an underline here and say, okay, well, I should have rounded this to 3 sig figs. So 1, 2, 3. Okay. Now that I did that for magnesium, I need to do that for the other reactant, in this case, oxygen gas. And so we start with 10.5 grams of oxygen gas, so 10.5 grams of O2 gas. Okay. Now here's where we got to be careful. Okay. Here's where we got to be very careful. Okay. We have 2 moles of oxygen gas and not 1. Okay. So from the periodic table, I'm going to multiply 16 or 15.599 by 2. Okay. So the molar mass in this case, for every 1 mole of oxygen gas, I'll actually get 31.998 grams of oxygen gas. Okay, now if this was just pure oxygen, this would be 15.99, or if some people want to round up 16. But because it's O2, we got to multiply 16 by 2 from the periodic table. Okay. And so because now we're in moles, we're doing the same thing. We're going to relate our stoichiometry. And so if I look at this, for every 1 mole of oxygen gas, I get 2 moles of magnesium 2 oxide. Okay, so for every 2 moles of MgO, I get 1 mole of oxygen gas. Okay, in this case, you see that this matters now. This is not 1 anymore. This is actually, we're going to multiply by 2. And so if I plug out my calculator and take 10.5 divided by 31.998, and I multiply that by 2, I should get around 0.65629 moles of magnesium 2 oxide. Now again, because of 3 sig figs, I'm just going to underline here, reminding me that I need to, my answer should be in 3 sig figs when it comes onto the theoretical yield. Okay, so now that we've gotten to this point, all we do is look at the number of moles and see which one of these reactant actually produce the lowest number of moles. Okay, in this case, you could definitely see that 0.4155 is less than 0.6526. It's the least. And so in fact, magnesium will actually be my limiting reactant. So magnesium is equal to my limiting reactant. So in this case, magnesium is my limiting reactant. Okay, and this is the general process of finding your limiting reactant. Okay, now how do you find a theoretical yield? Well, remember we said that your theoretical yield is based off your limiting reactant, and that's the one thing if you need to take away from this video. Your theoretical yield is based off your limiting reactant. Okay, and so if I look at this, well, my limiting reactant is magnesium. And so the amount of moles that it produced, this is actually my theoretical yield. Okay, the amount of moles the limiting reactant produces your theoretical yield. Now, a lot of teachers like your theoretical yield to be in grams, okay? And so if I look at this, my theoretical yield is actually 0.41555 moles of MgO. I'm just going to simply convert this to grams, okay? Because that's just the convention. Some teachers will actually tell you, well, what's the theoretical yield in grams? But for this type of problem, we're just going to assume that the teacher wants it in grams, okay? And so if I have 0.455 moles of magnesium oxide, well, I simply need to use the molar mass, okay? And so we could say for every 1 mole of MgO, I'm going to look at the periodic table, add magnesium, which is 24, to oxygen, which is 60. And so if I add those, I should get around 40.304 grams of magnesium oxide, 2 oxide, okay? And so when I look at this, all I'm doing is simply multiplying 0.455 times 40.304. Okay, now remember I underlined this third digit here. And so when I multiply that, I should get about 16.7 grams of magnesium 2 oxide, and this will be my theoretical yield. Okay, and notice how the underlying procedure works. Well, it keeps me to remember that actually should round to 3 significant figures. So again, your theoretical yield is based off your limiting reactant. So whatever number the limiting reactant gives you is your theoretical yield. In this case, we just converted to moles. Okay, we just converted to grams, apologize. And then the last thing to determine the percent yield of the reaction, well, we know the percent yield is defined as actual divided by theoretical times 100%. Okay, and so remember this. Okay, Remember we talked about the actual yield actually being given. They're always given. And so we have 11.9 grams of, the actual is 11.9 grams of magnesium oxide. Okay. And the theoretical is 16.7 grams of Mg, magnesium 2 oxide. Okay. Keep on saying magnesium oxide. And we're going to simply multiply that by 100%. Okay. And so when I plug this in my calculator, I should get around 71.3%. Okay. And notice again, my grams of magnesium 2 oxide will cancel out. Okay. And that'll just leave me with percentage, which is exactly what we want. Okay. Now, one thing I want to mention before I go. Okay. If your actual yield is bigger than your theoretical yield, you've done something wrong. Okay. If your actual yield is bigger than your theoretical yield, you'll get something wrong. Okay. Because think about it. If my actual yield was 16.7 and my theoretical yield was 11.9, I will get something over 100%, which does not make any sense. So again, if your actual yield is greater than your theoretical yield, you've done something wrong. But again, this is a general procedure behind finding limiting reactant theoretical yield and percent yield.